Okay, so if populations tend to fluctuate in size, what might that be described? If populations were to tend to fluctuate in size, it sounds like somebody else is.
Populations tend to fluctuate in size. What does that mean?
Maybe that's an inference, or could that possibly be an observation? Yeah, it's an, which one though? The second one, okay? So when survival is not at random, that might be describing an observation or an inference. And then which inference then? 1, 2, or 3? 2. Okay. And then just a brief summary of what we've done so far is I don't think we talked about observations 4 and 5. Those are probably blank. Okay? Because I think with my presenter, it might have skipped ahead for some reason. Don't know why, but we will take a quick look at those. Next week, we see what's expected of us. We start the school year with 3 short weeks. Of course, this one, next week is a short week, and then the following after that is another short week because of the Labor Day holiday. So that's why you see Friday the 6th, because that will be the next time that you're in here on a Friday is on September 6th. Okay? Because, of course, a week from today, we don't have classes. Okay? Because that's leading into the Labor Day holiday. It'll be it'll be August 30th, but we're not here in class. Okay? A question about the vocabulary. I think I had counted, 20, 21, 22 terms or something to that extent. Okay? So let's look at it this way. It's 15 questions over the first 18. Make sense? So that means that there are 15 questions, but there's 18 selections. Okay? So keep that in mind. Okay? Make sense? All right. Now, when we look at this, okay, when these resources are limited, like food and habitat, we had discussed that the idea that probably which observation is the best one that would describe what evolution / natural selection would be. 1, 2, or 3? Probably not 2, because, well, it could be. We think what we said in class, okay, this observation number 3 is probably the most important. I guess I thought that said inference, but observation number 3, I would be led to believe is probably the most important one. You do realize you could see that on the Science Channel, right? Okay. All right. So this I don't think you have down. Unless we were talking about me holding that textbook up with that of the zebras, but I think we were just talking about just the stripes on them. Or did we do that? You do have this. Okay. Then one of the aspects that for some people, this just really maybe makes them upset to a certain extent, and that would be observation number 5. And what might that be? Why is that maybe make you a little upset or disgruntled? Okay, let's just use a family reunion as an example. So we can say maybe, probably aunts are maybe really good at this. Who can we pick on? Okay? So is that where people say, man, you look just like your mom? No? Okay. Well, then we can't pick on you then. Does that sound familiar to anybody else? Okay? So, oh my, you look just like blank. Okay? Well, we're talking about parents though. Okay? So, with that, not as many distractions in this class? Not as many distractions in this class? Oh, a little different than your other science class? Oh, which one do you like better? Why is that? No, I'm just asking a question. Oh, okay. All right. Okay. I was under the impression when I looked at the computer that we did not have these observations. That's why we went over those. Okay. So switching this up, when we look at next week's schedule, one thing we haven't started with was we're supposed to start sight today, but we're just not quite going to get to that. We will start with next week. Okay? So one of the things I see we're trying to multitask. One of the things in a class like this, you can fall behind, and if that happens, sometimes bad things can happen. And you're making that choice. You're choosing to do that. Yes, no, or I'm choosing to do this.
I'm taking my notes on my computer.
Okay?
I lost my folder.
All right. Well, that's all you got to say. All right. So we got to get up to 25 minutes, I believe. So I will start that here shortly. We will wrap this up, and then if there's time, we will move on to that of eyesight. Please move that, please. Thank you. So we left off with discussing that of, I don't know if they gave a specific example, whales. I think it was blue whales. And one of the things that we left off with, their success story is being able to dive into deep depths of water. And we left off with saying it's not because they move their tail side by side, right? No, it's up and down. Okay? Fish move them side to side. Mammals will move them up and down. Okay, but it's not their tail movement that allows them to dive to great depths. What is that?
Their lungs collapse.
Lungs collapse. That's right.
Was 13 feet tall. They go, how deep they go. But your local Geico office.
Cool.
Remarkable. Oh no. Did you hear something?
Geico. 15 minutes could save you 15% or more on car insurance.
In the world of big, nothing on land has ever topped the sauropods. A plant-eating subgroup of dinosaurs, sauropods roamed the entire globe 200 million years ago, ranging up to 130 feet long, nearly the length of the White House. They set all the records for land animal size. They were even too big for T-Rex to attack.
We don't find very much evidence of big sauropods being attacked by big predatory dinosaurs. Things like Tyrannosaurus rex, be up to 30 or 40 feet long and maybe 7 tons. These were fearsome animals, but they're just no match for a full-grown sauropod.
These beasts were so much bigger than anything else that has ever lived on land that scientists knew the combination of factors that produced them must be unique. What was the secret of the sauropod's success?
This is Brachiosaurus. This animal is 75 feet long, 45 feet tall, and weighed about 30 tons.
Evolutionary biologist Matt Wadel has been working at the riddle for years. All the conditions had to be just right to produce this freak of nature. He picked up his first clue when scientists discovered that the Earth in the age of dinosaurs was very different from our own.
Sauropods almost lived on a different planet, not separated from us in space, but in time.
What made the planet different was the atmosphere. Recent analysis of fossil records suggests that carbon dioxide levels during the Triassic period, just at the start of the age of dinosaurs, soared to the highest levels ever. As a result, plant growth exploded.
When we grow plants today, under those conditions, they grow to almost double the size.
More carbon dioxide-breathing plants meant more food for plant eaters. And there have never been vegetarians who ate more than the sauropods.
For the very largest sauropods, the daily requirement for food was probably on the order of a ton of vegetation every day. Their heads are just biting machines. Not only did they not chew their food, they couldn't chew their food because their teeth didn't meet up the way ours do. They could just shovel it in and keep getting bigger.
It took relatively little energy for the sauropods to eat. One reason why plant eaters have the potential to get bigger than meat eaters. But as they evolved through millions of years, their growing enormity meant they needed gigantic muscles to move heavier and heavier bones, including the seemingly impossible sauropod neck.
Some of these necks were 40 or maybe even 50 feet long. Now, how does an animal hold up and support and move around a neck that's so long?
Today, the largest neck, at 7.5 feet, belongs, of course, to the giraffe. But giraffe bones are heavy and restrict movement. And sauropod bones dwarf them.
All right, that looks great. This is a neck vertebra of Supersaurus. This is the largest vertebra that we have ever found on Earth. It's 4.5 feet long. Now let's see how that compares to a vertebra from the neck of giraffe. This is one of 7 vertebrae from the neck of a giraffe. This is one of 15 from the neck of Supersaurus.
If sauropod neck bones were as dense as a giraffe's, the 15 vertebrae strand of Supersaurus would weigh more than 10,000 pounds. How could the Supersaurus lift bones so massive with neck muscles so relatively slender? Because the bones have turned to fossilized rock, their weight in life is unknown. But Wadel learned that a graduate student at Brigham Young University in Utah, Brooks Britt, had been using scanning technology on dinosaur bones.
From Diplodocus.
Britt suggested that Wadel scan neck bones to see if subtle differences in the fossilized rock could reveal the bone's original structure.
Nobody's probably scanned a Diplodocus vertebra that's in this good a shape.
The CAT scan will allow the first look ever at the interior of this 145-million-year-old Diplodocus neck bone. The different densities of rock within the bone are invisible to the naked eye, but the scanner clearly reveals that the bones in life were feather light.
There's cavities all through this.
Like car tires, the bones are pneumatic. They are 60 to 70% filled with air. Wadel suspects that the bones were not only light and easy to lift, they also helped get oxygen directly to the muscles, fed by a system of air sacs throughout the neck, similar to birds today.
Sauropods were probably about 10% lighter than they would have been otherwise. Now those effects ripple through the entire biology of the animal. You don't need as much oxygen. You can grow faster because you don't have to put on as much mass.
because they're hollow doesn't mean the neck bones aren't strong. Air-filled cavity design is widespread in engineering, from sneakers to the strong neck-like framework of a construction crane arm.
The material that's get replaced is not serving any structural purpose. Bighorn sheep are butting heads at very high velocities, very huge forces involved. Their horns are pneumatic, so pneumatic doesn't mean weak.
The sauropods had hit on just the right mix to become a freak of nature. Hollow bones, plenty of food, and a huge size to deter predators. They had everything going for them.
You've got dinosaurs all over the place. You have big ones, you have small ones, some of them eat meat, some of them eat plants. Everything's going just fine because they're well adapted to their environments. But then all of a sudden the rules change.
65 million years ago, striking with the energy of 100 million tons of TNT, an asteroid brought the reign of the dinosaurs to a sudden, shocking end. The heat pulse from the blast circled the globe and raised the temperature to 1,300 degrees Fahrenheit, killing the biggest dinosaurs and more within hours. The world was an oven, set on broil. The abundant vegetation was gone.
All of the big animals on Earth were at a huge disadvantage because they were big. Because they needed so much food and there was so little food around, they couldn't survive. Mammals, on the other hand, found themselves at a huge advantage because they were so small.
Every species over 20 pounds, 70% of all life on Earth, went extinct. The conditions for life on Earth were radically reset. Suddenly, tiny warm-blooded mammals, the ancestors of rodents, found their ticket to success. Today, rodents are found on every continent but Antarctica, in over 2,000 species with billions of individuals. And their descendants, every mammal on Earth, including us, would fill up every size niche in the world. Strange story of size. The amazing, size-changing wood rat.
Well, wood rats are probably one of the mammals that are most sensitive to temperature.
Bushy-tailed wood rats are small where the climate is hot, and 3 times the size where the climate is cold.
So let's go ahead and where? The animals here in the southern part of the range in the Sangre-de-Cristo Mountains in New Mexico are the smallest. If you go up to the northern part of the range, Canada, 204, you'll find animals that are about 3 times the size.
Wood rats even live in one of the hottest spots on Earth, Death Valley, offering a hint of how those earliest mammals survived when most everything else died in the wake of the asteroid hit.
In Death Valley, for roughly 3 months, it's above lethal every single day. So how are the animals able to get around the fact? Well, for one thing, they're nocturnal. But that doesn't help much when nighttime temperatures are still 118. It's still above lethal.
Smith made repeated ventures into the blistering heat of Death Valley and uncovered the wood rat's survival secret.
The animals build these enormous dens, and we found to our surprise by burrowing deep enough in the ground, some of these animals were able to get to a place within their den where the temperatures were 36 degrees Fahrenheit, cooler than the outside temperatures, which is an enormous amount. It gives them an edge where they can actually survive.
For the wood rats in Death Valley and those first mammals, being small was an advantage. They were able to hide out and survive on little until food sources returned and life on Earth could spread again. mammals radiated out into thousands of species, from leopards to rabbits to people. And 3/4 of those species have grown larger over time.
A lot of groups, when you look at the sequence of fossils over time, you see that within a species, animals are getting progressively bigger. It's not true for all groups, but it's true for quite a few of them.
For example, horses in North America have a beautiful fossil record documenting ever-increasing body size over tens of millions of years.
In an evolutionary sense, there's always selection for larger size. You're better at getting mates. You're better at fighting with other individuals if you're a carnivore. You're better at stealing carcasses from other species. There are lots of reasons to get big.
Blair von Valkenburg teaches ecology and evolutionary biology at UCLA. An expert on wolves, past and present, Valkenburg argues that with size comes risk. As meat-eating mammals grow larger, they reach a tipping point.
It's really interesting. Mammalian carnivores fall into two groups, basically divided by body size. Everything that's less than 44 pounds and pretty much everything that is above 44 pounds.
Above 44 pounds, a meat-eating mammal has to change its diet to eat much bigger prey. Otherwise, it has to hunt too frequently.
Imagine a day in the life of a wolf. And the wolf says, I'm going to eat mice today. So he goes out and hunts, catches a mouse. Yum, that's good. But I'm still hungry. So let's get another mouse. Still hungry. Another mouse, and another mouse, and another mouse. Every mouse he catches, he's expending that energy that he gained catching that next mouse. So he can hunt all day and never get full, never be satiated.
The balance between size, food, and the energy required to get it means that no land mammal carnivore could ever be bigger than 2,400 pounds, about 700 pounds heavier than the heaviest polar bear.
Animals can't get infinitely big. There are all kinds of factors that come into play. Animals have to be able to get enough oxygen to their tissues to keep their tissues alive. If you're really big, that's not very easy to do. Animals have to be able to find enough food to feed themselves. If you're infinitely big, there's just not enough food in the environment. Also, most animals have to move around on the ground and support their body weight. And if you're too big, that just can't be done.
The dire wolf evolved about 9 million years ago and grew to 150 pounds, twice the size of today's gray wolf, which made it an evolutionary success for a time. But the dire wolf could not adapt when the change in climate killed off some of its prey. After 100,000 years of coexistence with its gray wolf cousin, the big-eater dire wolf went extinct 10,000 years ago. Meat-eating dinosaurs, of course, got much bigger, but even an energy-efficient reptile like T-Rex bumped up against its maximum size.
Tyrannosaurus rex was probably limited in how big it could get because it relied on meat. And there are studies that suggest that Tyrannosaurus rex was as big as a carnivore can get. Sometimes you can't just keep on getting bigger.
What about human beings? Are we evolving bigger and taller all the time? And are we therefore at risk for extinction?
There's no question that over the last 100 years, people have been getting taller, especially in North America. If you go to an old colonial home, the doors are shorter, you feel like a giant walking around in there. But is that a result of evolutionary change, or is that just a result of differences in nutrition? That's something we don't exactly know.
Human height is something of a mystery, and the story is full of surprises, starting with the fact that we are now shorter than we were 50,000 years ago.
Believe it or not, agriculture was not progress.
In general, I prefer taller men. If he has a larger and stronger physical appearance, it just looks better.
I like them to be bigger than me to feel more protected.
It's just more attractive.
Just something kicks in.
Mate preference is one of those things where people don't always have all that much insight into their own preferences.
Evolutionary psychologist Robert Kurzban studies human mate preference, gathering data in the controlled conditions created by a hurry date.
You just have 20 minutes, and of course this makes it an interaction where first impressions make a big difference because there aren't second impressions.
What counts? Sparkling conversation?
As far as we can tell, the conversation doesn't matter at all. It doesn't matter what they're saying. It doesn't matter. What they're choosing on are these physical features, how skinny you are, how tall you are.
In choices influenced by deep evolutionary drives millions of years old, men desire women with low body mass index, the thin ones, and women desire men with size.
Just like in the non-human animal world, when people are looking for a short-term mate, people look for those things that correlate with good DNA. What we found was that the taller a man was, the more likely he was to get selected by women.
A recent study of a West Point graduating class showed that the taller the man, the more children he has, mostly because of marrying a second time later in life. All across the globe, the story seems to be the same.
Everywhere in the world where there are people who arrange marriages, one of the criteria that's always given is that the husband should be taller than the wife. Taller individuals might be sexier in that sense.
Biological anthropologist Barry Bogan has been unraveling the mystery of human growth at the University of Loughborough in England for over 20 years, starting with the earliest known human ancestors.
What I have in my hand here is a cast of the femur or thigh bone of Lucy, the famous Australopithecus afarensis. Lucy and her kind were quite short, shorter than modern-day pygmies, under even 4 foot 8 inches tall for the men. You can see that this femur would fit in just about here.
From that humble beginning, humans grew until they reached an average of 6 feet tall. 50,000 years ago. It turned out to be a high point that we have yet to touch again.
Things change, and we see a decline in stature, down to 5'3" adult males.
What could cause this reversal of fortune? As elsewhere in the story of size, a changing environment. It killed off the prey humans fed on and forced them to find new sources of food.
People were not eating as well. People who previously hunted and gathered their food just couldn't find enough. And they started to harvest foods that probably were growing in their garbage piles. The seeds sprouted up and they said, hey, we can eat some of our garbage.
It was the start of agriculture, and for a long time, it was a disaster.
Believe it or not, agriculture was not progress. Agriculture narrowed the variety of foods people ate. That resulted in nutritional deficiencies and smaller people.
Good nutrition would be scarce, and height would remain compressed until the late 19th century, when better foods, improved sanitary conditions, and healthcare took the brakes off human height. We caught up fast, and now the developed world averages 5'9" for men, 5'4" for women. Not a record, but a best in the modern era, and the trend is definitely up. Everything seems to be in place for humans to continue to grow. Nutrition, sexual selection, and the general tendency of mammals to size up over time. So, are we headed for the land of the giants?
If we were to come back in 200 or 300 years, the human species would probably be 7 or maybe even 8 feet tall. It seems hard to believe, but the fact is, humans have been getting taller every generation. It's a combination of nutrition and genes, but that combination is making our entire species bigger than they were.
But not everyone agrees.
Will we be 7-footers, 8-footers, and taller? I don't think so. There is a cap on healthy human height.
Bogan points out that above 7 feet, people today encounter increased medical problems associated with their height. He believes that the greatest average height we can most likely achieve is a healthy 6'2" for men and 5'8" for women.
If I live another 100 years, you can come back and ask me if I was right or wrong.
As human beings and all life on Earth moves to the future, all the factors affecting body size, from mating to predation to environment, will continue to be in play and are likely to produce amazing and unexpected results as size continues to evolve.
So as you can see, we're not going to get to the site video. Excuse me, we'll save that for Monday. So anyone want to take a guess why, when you look at human height, what might be a reasoning that you can think of that being over 7 feet might be a disadvantage? I mean, it could be an advantage, but maybe it's a disadvantage. Okay, so when you look at the different types of joints that you form, just because you put on more muscle so you can actually get taller, muscle weighs quite a bit. So when you put that on your joints, that's certainly going to make someone less mobile. Now, when you look at every Saturday and Sunday during the football season, you might think, well, man, those individuals move pretty fast. And I would agree. But eventually, as individuals age, that could present problems. It doesn't mean that it does, but it just means that it could. Okay, so if giraffes can only have such a long neck, why can a supersaurus, which was within a class of what we call them sauropods, okay? How is that possible for those animals to have such a long and large neck? Because when you look at bone tissue, typically it should be more dense than that, with that of marrow on the inside. But these bones were what we consider pneumatic, so they are filled with air cavities. And one of the aspects that is important is because that's similar to an avian characteristic. So not only are these animals breathing in air with their lungs, how is that supplemented in these sauropods? The narrator said, what? We said it already, you just need to correlate the two. We said that if they're pneumatic bones, yeah, because they're actually extracting oxygen or air, whichever, from those bones to supplement their blood supply. Okay, so once the dinosaurs were erased, how was it that the mammals could be so successful then? Well, and it would be a combination of two things. Yes, they could burrow underneath like the wood rat does, but when an organism becomes smaller, what type of resources does it need? A lot or not as much? Because if you're smaller, well, then you don't have to take in as much oxygen and then nutrients as well. Okay? So what is it that really will limit the size of any organism, whether it's an animal, whether it's a human, whichever? There's three characteristics. Oxygen's one. Okay? They're going to have nutrients. Okay? And then they said you need to be able to go from point A to point B, then maybe to point C, point D. So that's just not very easy to do for some of these organisms that are quite large then. So yes, oxygen, food / nutrients, and or movement. Okay, we will pick up with this next week.